Hi folks, and welcome back to Functional Analysis. In the last video we finally introduced the important concept of the Hilbert space. So the Hilbert space, or a Hilbert space, is a inner product space which is complete in the induced norm, the norm induced by the inner product. We had one example up front. This was Cn, coordinate space, n-dimensional vectors with complex entries. That space equipped with the dot product, which is an inner product, is a Hilbert space simply because it's a finite dimensional space. It's a consequence of the equivalent norm theorem. Now the second example that we will continue now is written here on the page. We go to continuous functions on 0, 1, equipped with this inner product is written up there. And as it turns out, that one, this space here, that inner product space, is not complete, hence it's not a Hilbert space. We have to complete the proof now. So what we have to do is we have to construct a sequence which is Cauchy in the induced norm, the norm induced by this inner product, but which does not converge to a limit that lies in this space, aka which does not converge to a continuous function. Okay, here's the candidate. I discussed it last time. Here's the picture. So it is a piecewise continuous function. It is 0 up to 1/2. At 1/2 minus 1/2 all the way up to x equals 1, it's constant 1, and in between you connect with a straight line so that the whole thing is continuous. And indeed you can see that this is continuous. If you plug in here x equals 1/2, you get 1, and that is precisely also the limit that you get from the right as you approach 1/2. Okay, so this is clearly a continuous function. Now observe that pointwise as n goes to infinity, so this would be a problem in say real analysis, fn of x pointwise as n goes to infinity, it converges to a piecewise constant function, but which is discontinuous. So 0 away from 1/2 and 1 above from 1/2 all the way up to 1, and at 1/2 the value is equal to 1. Okay, this you can spot here in the picture. It's because this window here shrinks to 0, so that red part here, it will get steeper and steeper until you finally end up with them that two straight line piece function. Okay, this one here, that limiting object, we will call f of x. Okay, and f of x is not a continuous function. However, this limit here, the pointwise limit, is not enough to conclude that that space up here is not complete, because we have to make sense of limits in the norm induced by this inner product. Okay, so we have to address now this question. Good, let's do it. So first, note that let's show that fn of x as n goes to infinity not just pointwise converges to that limiting function f, but also in the norm induced by the inner product. So for this reason I have to estimate fn x minus f of x dx. Right, keep in mind the norm induced here in our case would be f is the square root of ff, which is 0, 1 fx squared dx, and then a square root. Okay, that's why you have here the square. Okay, so let's look at this. Now this is an easy computation. You just use the formula that you have for both fn and for f. What you will realize is there's only a non-zero contribution in this interval. Why? Because if you exceed 1/2, both functions are equal to 1, so the difference is 0. And if you are to the left of 1/2 minus 1/n, both functions are equal to 0, so the difference is well, also 0. Okay, so you have this up front, and now it's really a calculus exercise. You plug in the formulas for fn and f, you compute the integral, and maybe I will skip this step. Nevertheless, you should check at home after an easy change of variables it becomes n squared u squared du, and that whole thing is 1 over 3n. That's an exact computation. As n goes to infinity, this converges to 0. Okay, so you indeed have also not just pointwise convergence of fn to the limiting function s, but also in the 2 norm induced by that inner product. Okay, on the other hand, we have to check that this is indeed a Cauchy sequence for any n m integer above 2. We find, now this is a similar computation, so now you look at fn of x minus fm of x squared dx. Again, you're gonna plug in formulas, but it's a bit now, how to say, it's a little bit more difficult because you would have to assume, say, n is bigger than m so that you can actually operate with the formulas. If you don't want to do this, you can just roughly estimate this, because both quantities fn and fm, they're always below 1. So if you use triangle inequality inside, you can get that this is at most 1 plus 1 squared. Use the triangle inequality, then the result gets squared. Each quantity is at most 1, so get 1 plus 1, and the whole thing squared gives you 4. And what about the limits? Well, the upper one is again 1 over 2. And for the lower one, you have to think a little bit, but this I leave to you. Just draw a picture. This is the minimum from 1/2 minus n and 1/2 minus 1 over n. Okay. Now this here you can compute explicitly, and what comes out after some algebraic simplification is the maximum of n and m times 4, and then the product n over m. Okay. Yeah, but now when n or m go to infinity, this quantity will go to 0. So that sequence is Cauchy. Okay. However, if for some f infinity in C0n we have that fn minus f infinity in the 2 norm induced by the inner product, as n goes to infinity, goes to 0, then by uniqueness of the limit, we must have that limit f infinity is precisely equal to the previously constructed f. Yeah, but that previously constructed f was not continuous. Okay, so there's a contradiction. Hence, that Cauchy sequence is not convergent. Okay, in this inner product space. Hence, C0, 1 with that inner product up there is not a Hilbert space. Okay, good. There's many other ways how you can prove that this guy is not a Hilbert space. We did it with that function that converges to that, piecewise constant piece, 0 here, 1 there. You can operate also with those triangle hats, so functions that are like this, and then when n goes to infinity, the pace shrinks together, so that essentially you converge on a function which is 0 everywhere except at one point. Okay, again, that thing wouldn't be continuous, and you get your contradiction. All right, now let's discuss a positive example, a very important positive example of a Hilbert space, which is small L2. So remember, small L2, those are as a sequence space, those are square summable sequences. This is an inner product space. We mentioned the inner product earlier on. This is just, in a sense, the dot product, but you run the summation all the way up to infinity. It's written here, and now the claim is this one is a Hilbert space. Okay, so what we have to do now by definition is we have to pick an arbitrary Cauchy sequence and show that that guy is convergent in that space. Okay, so that's what's written here. Let xn be a Cauchy sequence. Now here, careful with the notation now. So small l2 itself is a space consisting of sequences. That means each vector, each point in the space is a sequence. Okay, so now if you take a sequence of points in that sequence space, that means each term here of my Cauchy sequence is itself a sequence. Okay, so that's why by default in our notation we will have to operate with double indices, and that's what I wrote here. So noting that each term xn is itself a sequence, and we write it with the double index as written here. Okay, good. That's the starting point. Now, here's a strategy that we will actually encounter again in chapter 3. How do you show that something is complete? Well, pick a Cauchy sequence. Now you have to find in the first step a limit candidate. Okay, I will show you how to do this from one example to the other. Once you have that candidate for the limit, then you have to show that it is actually in the space that you want, not unlike in the previous example where that f was not continuous. If you want to show it that things are complete, you have to show that the limit is in that space, and then you have to show rigorously the convergence of Cauchy sequence to the limit in the appropriate norm. Okay, and this is what we will do. So it's a 3-step process, in other words. Good. Let's get started. So this will take a little bit of time. So fix up front k in n and consider this sequence x and k where I run over n and not over k. Okay, n1 infinity. This is a sequence of either complex numbers or real numbers depending on your field. Then for any nn in n, so here's an estimate, x and k minus x m k. Okay, there's some simple algebra up front. I can square it and I can take the square root of it. Nothing changes by doing this. But now why do I do this? Well, because I have to operate with the 2 norm, because I know that xn is a sequence in the 2 norm, a Cauchy sequence in the 2 norm. So that's why I do this surgery. This is at most xn of k minus xm of k squared. And this guy, right? So this should be clear why this is true, because whatever k you choose here, it will certainly be contained as one term in this infinite sequence, right? So definitely adding to that one term all the other ones will give you an upper bound, and that's precisely what's written here. Okay, but now using the definition, the notation that we have up here for our xn, this guy is precisely the 2 norm of xn minus xm. Okay, and of course this gets small when n and m become large, because xn is a Cauchy sequence. Okay, so by this we conclude that xnk n1 infinity is Cauchy in F. Yeah, but our scalar field is either the real number field or the complex number field, which is complete, right? It's Cauchy and so convergent in F. Let's write it as xn of k as n goes to infinity goes to yk as n tends to infinity. Okay, and we define that will complete step 1, find a candidate, y as the sequence formed of all those yks. Okay, that is step 1, find a limit candidate. How did we do it? Well, we look at, in some sense, the coordinate sequences. You fix the k and run the n only out. You exploit the fact that your initial sequence was a Cauchy sequence using this simple inequality there, and then you heavily rely on the fact that your underlying field is complete, either complex number or real numbers, and that gives you a limit candidate, and this will be the y here. And as we will see, y will do the trick. Okay, but we're not there yet. Next, now we have to show that, well, this object y is actually in small l2. Okay, good. Let's do that. Next, given that xn is Cauchy, What does this mean? I will just use the definition. For any epsilon positive, there is capital N, which of course depends on epsilon, so that difference here becomes small. Xn minus xm in 2 norm becomes small whenever small n, the indices, and small m exceed that, well, quantity capital N. Hence, for arbitrary capital M and small n in n, let's start with this. So we want to show that our candidate, that sequence y on the previous slide, is in small l2. So what we will do is, instead of running the sum all the way up to infinity, which will throw a serious wrench in your calculation, you truncate it at an arbitrary finite capital M, okay? And now you show that for any capital M, well, whatever comes out here is finite, and then you push capital M to infinity. That's sort of the strategy. Now, how to do this? Okay, you will use, well, Minkowski inequality. So you first add and subtract a bunch of zeros in this fashion. So first there's small n, small k, added and subtracted, and then added and subtracted are x with capital N and small k. Okay, and here is a square root. Okay, so that's an equality, and now you apply Minkowski inequality. That guy also works for the finite sums, doesn't have to go all the way to infinity. So you chop off here and you chop off there, and that gives you, by Minkowski, the discrete version of Minkowski as I call it in the lecture notes, this gives you k1m yk minus x and k squared square root, and then for the other one, well, there would now be a sum over the x and k minus, well, x with the capital Nk, but there you can add infinitely many terms, so you run the k index all the way to infinity, and then this is just this 2 norm, okay? And the same thing you can do for the last term. In the first term, you keep the capital M, the truncation parameter, in place. For the other two, you already push it to infinity. Okay. Now, what do you know? Well, we have that something is a Cauchy sequence. So, which of these quantities are small? Well, the middle one, xn minus x small n minus x capital N is less than epsilon in 2 norm for n above capital N. That's because of Cauchy. And by the convergence, remember, x and k minus yk goes to 0 as n goes to infinity for any fixed k. This is, by the way, one of the deep reasons why you want to truncate it here, right? So for any fixed k, that means you don't want to let k go to infinity, because then you don't have two competing scales. That's why you do this. Okay. As n tends to infinity, you have that limit n goes to infinity k1m yk minus x and k squared square root is equal to 0. Okay, good. That's easy. Hence, for any capital M, a natural number, we have just proven the following bound. This is less than or equal to, so the second quantity here, this will give you the epsilon. The third quantity you just leave as is. And the first quantity, as you push n, small n to infinity, which you can notice, by the way, the left-hand side is completely n independent, it will go to 0. Okay, so you have this, and this means, of course, this is a finite quantity. Notice the right-hand side is completely independent of capital M, right? And that's what you want, because now you have this bound for any fixed M, so in particular in the limit. Thus, our limit candidate is indeed square summable. Okay, that's the second step of the three-step process. Now what remains to show is that, well, it actually converges in the small L2 norm to the desired limit. Okay, good. It now remains to show that xn minus y2 norm goes to 0 as n goes to infinity. And then you're done. To this end, very much like above, in step 2, let epsilon positive be arbitrary and choose capital N and epsilon positive, so that you're going to again exploit, of course, that your sequence is Cauchy, so that difference is small whenever n m above capital N. Okay, then essentially copy paste of the step 2 is just we don't have to insert that many terms. Then for arbitrary capital N and small n with small n above n, again Minkowski K1m, you want to estimate this difference. Yeah, so the difference is here now to the step 2 that the xnk already appears on the left, because you want to estimate the norm of the difference, right? So that makes sense. But now you again insert a 0 here in the form that you insert an xmk, say, squared, and then the rest would be xmk minus xnk. There you sum out all the k's, so you have xm minus xn, because over this guy you have control, right, because it's Cauchy. So less than epsilon, this is coming from here, and the first one you just leave as is. K1m yk minus xmk squared square root. But now look, the left hand side is m independent. I have only the m here, so what I can do is I can send m to infinity. I know by the pointwise convergence of xmk to yk as m goes to infinity for any fixed k, this difference here will go to 0 for any fixed k, so also when you sum over finitely many terms. Okay, so this will go to just epsilon. All right, hence for every capital M in n, when small n is above this capital N, you have k1 m yk minus xnk squared square root less than or equal, say, epsilon. And that's all that you need. So indeed y minus xn is less than or equal to epsilon for n above capital M, and thus by definition of convergence y minus xn in 2 norm goes to 0 as n tends to infinity. Okay, and that completes the 3-step process. All right, so strategy was as follows. Keep that in mind. We will encounter this again in chapter 3 in the Banach space chapter multiple times. So we had a space here up front with a small L2. We already knew that this is an inner product space because we discussed this inner product here in our examples up front. And now the claim was, well, actually that inner product induces a norm and the space small L2 in that norm is complete. So in short, small L2 of that inner product is a Hilbert space. How to do it? There's 3 steps. You start with a Cauchy sequence, arbitrary Cauchy sequence. Then you have to somehow cook up a limit candidate for the Cauchy sequence. Once you have that idea, you have to show that that candidate is actually, well, in the space that you're working. with, and then you have to prove the convergence in the appropriate norm. And that's what we did. We started by Cauchy sequence here. We cooked up a limit candidate by essentially falling back to the scalar field. That's what always happens in the sequence spaces. You always fall back to the scalar field. Okay, that produced us here this candidate y. And then step 2 was to show that y is square summable, and that we did by playing around with Minkowski inequality essentially. The important feature here was you want to truncate your sums, all right? And that you needed because you have the convergence earlier on only, convergence is as n goes to infinity, but you only have it for fixed k. That's why here in your sums you cannot go all the way up to k equals to infinity. You have to truncate somewhere. And that all worked out nicely. Then we had that y is in small L2. Good, and then it remained to show that actually convergence holds in the 2 norm in L2. And that's very much the same argument. Again, Minkowski inequality with truncated sums, and then out of the computation at the end, you conclude what you need. Okay, good. That, I think, yeah, that is enough for this video. We will have many more spaces coming up. First, there will be, of course, in the exercises, there will be many Hilbert spaces that you need to check. While I write something down, I have to check that this is a Hilbert space. What we will do now here first in the next video is we will develop more theory, very important stuff, which is the Riesz representation theorem. Okay, but this I will discuss in the next video. See you then.